We're going to do a little bit of review before we get into the bulk of Chapter 12 by going over all the information that we've kind of discussed with quadratics so far. So we've got different forms of a quadratic equation, standard, factored, and vertex, and they all have their different uses. I will note I made a mistake here, so let's go ahead and fix that. That squared should be located here. So go ahead and make that adjustment. So standard form is our most common form for modeling, and it helps identify things like end behavior, y-intercept, and dilation, and we'll talk about those more in detail later. It's also the required form if we want to go ahead and try and factor our polynomial. Factored form is what we use when we want to solve a quadratic, and it also quickly shows features like roots, zeros, x-intercepts, which are essentially the same thing, and are the values we find when we solve the quadratic or the polynomial. It also shows us things like multiplicities, and we'll discuss that in more detail later as well. Vertex form is arguably the most useful form for graphing because it can quickly show features like the vertex, the axis of symmetry, the end behavior, the amount of dilation, and we can quickly solve for x and y intercepts from that form. So when solving a quadratic, we've got a few different options. Zero factor property is one that we've used a lot. We've talked about it many times, so I'm not going to go into a lot of detail here, but I will work through factoring each of these examples and then using the zero factor property really quickly. Now, we've talked briefly before about square root property, but we're going to dive in a little bit more in depth. If we're given x and k that are complex numbers, and if x squared equals k, then by using the square root property and square rooting both sides, we find that x can equal the square root of k or the negative square root of k. We'll either have a positive root or a negative root. So we need to consider both solutions when we are solving. So for example, I have x squared equals 5. Well, two things when squared will equal 5. If I square root both sides, x could equal the square root of 5 or the negative square root of 5. So I need to consider both as my solutions. Now, the key thing to remember when we are using the square root property is that whatever is being squared needs to be isolated before we take the square root property. So we're going to move our constants and our coefficients to the other side of our equation. Then we'll go ahead and apply our square root property. X is a positive or a negative square root of 12, and we can simplify the square root of 12 as positive negative 2 square root of 3. So again, we still have two solutions, 2 square root of 3 and negative 2 square root of 3. Here, the thing being squared is already isolated, so I can go ahead and take the square root of both sides. The square root of 18 simplifies to positive negative 3 square root of 2. And then now we can go ahead and isolate x. We'll add 3 to both sides. So we have 3 plus and minus 3 square root of 2. And then we divide at both sides by 2. And we get our value for x as 3 plus and minus 3 square root of 2 over 2. And again, that's two solutions, one with the plus 3 root 2 and one with the minus 3 root 2. Here we need to divide both sides by 2 before we take our square root property. X minus 5 equals a positive and negative 6. We'll go ahead and add 5. So x equals 5 plus or minus 6. And again, this one we can actually evaluate. 5 plus 6 is 11. 5 minus 6 is negative 1. So x is 11 and negative 1. Here we have Galileo's formula for falling objects, as described as d equals 16t squared. If an item is dropped from the Leaning Tower of Pisa at 180 feet, we can substitute 180 into our equation, and we can go ahead and use our square root property to solve. Now, a couple things. If we want an exact answer, and we go ahead and square root, if we do it before we simplify, then we don't have to spend any time rationalizing because our denominator is already 16. And so we have positive and negative, the square root of 180 over 4, and we can simplify the square root of 180. It has a factors of 36 and 5, which gives us 6 square root of 5 over 4. And then we can reduce the fraction 3 square root of 5 over 2. Now we can ignore negative time, and so we just have the positive solution, 3 square root of 5 over 2. But the exact value doesn't do us any good. So instead, we can actually just go ahead and get a rounded value, which would be much more useful. So make sure you consider any rounding directions that might be given. And we don't need to simplify first. We can go ahead and just plug this directly into our calculator. And we get an approximation of about 3.35 seconds. Last but not least, we've got two more different cases here. When I apply my square root property, recall that when we square root a negative number, it's something that's non-real. And so you may recall from a previous algebra course that when we square root a negative number, we use the imaginary unit I. And I represents the square root of negative 1. And so this allows us to separate negative 15 into a negative 1 and a 15, which allows us to get the value of plus or minus I square root of 15. Here we have a pure imaginary number, which is part of the set of complex numbers. For g, we subtract 25. We square root both sides. And since our factors are negative 1 and 25, and both of those we get square roots, we get plus and minus 5i. And then we can subtract 5, negative 5 plus and minus 5i. And here we have a complex number in the form a plus bi, where negative 5 is the real part and 5i is the non-real part. But again, we still have two solutions, negative 5 plus 5i and negative 5 minus 5i.